Thank you very much for the introduction. I'm Shamim Nemati, Associate Professor of Biomedical Informatics at UC San Diego. I also wear a hat as a Director of Predictive Analytics at our hospital, UC San Diego Health. For the past 5 years, I've been teaching a course. It's called MED 277 at UC San Diego. It's Introduction to Biomedical Natural Language Processing with Dr. Mike Hogarth. And some of the slides that I'm presenting today are borrowed from Mike, actually. I also have a disclosure. I co-founded a company, Healthsigio, which is focused on commercialization of predictive analytics and AI in healthcare. All right, with that, today I'm going to talk about large language models, the notion of connectionism or neural language models, which was introduced actually in early 2000, and then sort of walk you through the historical progression of how we got to here, starting with some of the simplest connectionist models for language, word-to-vec, and getting into sequence-to-sequence models that tend to be important anytime you engage in machine translation or classification of text. And then this notion of attention that really captured everybody's attention in the past few years with the introduction of transformers and the rise of foundation models, these large language models, and then talk a little bit about ethical and legal considerations. In between, I will talk about some of the applications as we go through these topics. So my goal is to demystify these large language models, but as Arthur C. Clarke said, any sufficiently advanced technology is indistinguishable from magic. And even for those of us who have been part of the sort of history and we've watched the progress of modern large language models, it is still a little bit of a mystery. I guess there are things that comes with a scale, and as human beings, we are just not used to think about billions or trillions of parameters and what emerges once you put all of that together. All right, so feel free to ask questions along the way. I was mentioning earlier on that one of the challenges of interdisciplinary work is, people speak different languages, and sometimes they think they are talking about the same thing, but they actually are referring to different concepts. All right, so connectionism refers to use of multi-layered neural networks for language modeling. And, in the old time, when we were using computers to model language, we were dealing with this idea of one-hot coding, which if you have let's say, a vocabulary of size 10,000, a given word would be a 1,000 vector where you have a 1 at a particular location corresponding to that particular word in your dictionary. But with connectionism, that type of mapping changed into what is called representation of or activity of neurons in a neural network. And I get into that. And it turns out these representations, they capture what is called semantic similarity around words. So the meaning of words gets encoded into these word vector representations. And they have shown really a lot of promise in terms of things like text summarization, classification of text. But it turned out these type of representations were quite powerful. And in terms of generating text, they could capture so much of the information embedded in text in terms of the meaning of words, but also the sequence of relationship among words. And so that's how we got into large language models, and I'm going to walk you through some of that. All right, but before we get there, maybe I'll just provide a little bit of background on deep learning, this idea that you can use neural networks to do learning. And in particular, deep learning models, they follow this notion of distributed and hierarchical representation. And that idea really came from neuroscience. Back in the days when Hubble and Wiesels in 1960s, they were poking around cats' visual cortex, they realized that information processing in the visual system, humans or animals' visual system, it goes through multiple layers of processing, starting from retina where you have very simple detectors. These are things like color detectors or age detectors. But by the time you get into like V1 area, you start to see more complex pattern emerging, like the center out type of patterns, or neurons that respond to like stripes or sort of complex shapes. And by the time you go into higher levels, you see that these neurons, they start responding to more and more complex patterns. And the idea was that this is happening through a distributed sets of representations. So if you start with an image, that image is broken into its very basic components, the different colors or the edges, and then those basic components or features, they get composed, imposed on the top of each other, and that's how you get the emergence of, something like vision. So this idea of deep hierarchical representations is something that people try to emulate in computers. And this is an example of one of the first, what is called convolutional neural networks that people apply to classification of natural scenes. In these examples, they were trying to classify different faces. And so the convolutional neural network has several layers of processing. Each one of these layers, they have what is called local filters or feature maps. And once people train these type of models on the top of natural images, and they start interrogating the individual detectors or filters, they notice that at the very low level, we have like age detectors. By the time you get to higher levels, you have filters that are sensitive to different features, nose and eyebrows and mouth. And then at the higher level, the neurons, they become sensitive to specific types of faces. So there was a validation that the same sort of observation that you have in the visual pathways in primates, if you try to model that in silico, in computers, you also get those type of hierarchical representation. And so that's the notion of this deep learning and distributed hierarchical representation. And we're going to see how the same idea might apply to natural language modeling. So the basic idea here is that words with similar meanings are often used in similar contexts. Or in other words, a word is known by the company that it keeps. So the meaning emerges from the relationship between words. And so like, here's an example. I do a lot of research in critical care, and it turns out if you get a corpus of sort of critical care nodes and do some clustering on these nodes, it turns out similar words, they tend to show up in similar places, things like sepsis, infection, shock, or lung and kidney, the organ-related stuff, they might show up in the similar places. So that was an observation that people had. And so as I mentioned, with the old method of modeling language, essentially we had this notion of one-hot coding. Let's say you have a vocabulary of 10,000, or in modern natural language processing pipelines, you have a vocabulary of, let's say, 30,000 words. And a word such as heart is represented in terms of a one-hot coded vector, that there is one location for the word hot, and that's where you get one. And if you have the word lung, you have another sort of location where that's one, everything else zero. Versus this concept of word embedding essentially comes up with a vector representation of size, say 300 or 768, where you get a numerical vector of the following word. Let's say the word heart, you end up with a numerical representations. And these numerical representations are something that you learn using deep neural networks. And then it turns out the relationship between words is encoded in these numerical representations. So let's see how that happens. All right, before getting there, once we had the old way of using one-hot coding, there was a technique that was popular. It was called Markov language models. So the way they worked, basically, let's look at 3 examples here. Show me my directories, please. That's one sentence. Show me my files, please, and show me my photos, please. So if you think about these 3, if you want to model them, you have a sequence of words, show, me, my, and then you have three possibilities here. Directories, files, and photos. And then the last word is please. And if you have, let's say, again, a corpus of text, it might be the case that roughly 20% of the time the word directory shows up, 30% the word files, and the word photos shows up at 50% of the time. So here you have 7 vocabularies, and the Markov modeling was allowing people to model this. And if I wanted to generate text from this, I would just run the Markov chain forward in time. And then by the time I come here, because there is probabilistic, I would essentially flip a coin or sample and would generate my sentences. Another way of looking at this is in format of matrices and vectors. So again, let's say I'm at the word my, so the representation is 0, 0, 0, 1, 0, 0. And then you have the transition matrix, the Markov transition matrix. If you make the multiplication, it turns out you get the probability. And it's in this case, it's saying that there is a 0.5 probability that the word photos will show up, 30% probability for files, and 2% for directories. So this was fine when you had simple sentences. But if you have something like this, check whether the battery ran down, please, or check whether the program ran down or ran, please, depending on the context. It turns out the Markov chain gets a little more complicated because, so check whether and then you have the word battery and program, let's say 60% and 40%, and the word ran, but then depending on the context, you may have just please in this case, or ran down, please. Again, depends on the context. And so this is an example where if you want to figure out what should come here, you kind of need to know about whether you had battery before or the word program before. And sort of that complicates. So this is second order type of Markov modeling. And people, again, were trying to construct these massive matrices that instead of the single words and their transition probability, you have like tuple of words and their transition probability. And it turns out language is very rich. And in many cases, you really need to know about the context of a word, maybe in a very long sequences, to be able to model it. And it turns out that this kind of approaches, they weren't efficient. So here we are in year 2001, and a paper came out that introduced the first example of what is called a neural probabilistic language model. This is by Joshua Bengio and colleagues. And they basically said we can use a neural network to make one-step ahead predictions. So let's say you have a sentence, you have a series of words, let's call it WT, and then WT minus 1, WT minus 2, all the way back, depending on how long you want the context of your sentence to be. And so what you have here is essentially a feed-forward neural network that makes use of the context to make a prediction about the last word in a sentence. And this model was, again, presented in 2001. And it was quite revolutionary. But for those of you who are old enough, recognize what happened around that time. I just had started my graduate school, and I wrote my first paper focused on prediction of tornadoes. I was at the University of Oklahoma, and that was the interest. As we had data from National Weather Center at the University of Oklahoma, and they were interested in prediction of tornadoes and their patterns. And my advisor at the time, I recall, he told me, remove the word neural networks from your paper everywhere and replace it by the word machine intelligence. And the reason was that this field of neural network was entering sort of a winter season, and people were kind of weary that these methods, they don't really work. So this paper, I would say, got ignored a little bit for a few years, until here we are in year 2013. A group of people from Google in Mountain View, they proposed a model called Word2Vec. And the particular model that they were using is called a skipgram. So the idea of a skipgram is very similar. You basically, let's say you have a sentence, the dog chased the cat. And essentially using the words, let's say chased, you are trying to predict the surrounding words, the dog and the cat. And you might say, what a silly thing to do. Why would you care about that? It turns out, as I mentioned earlier, the meaning of words is linked to the company that they keep. So, in terms of semantic similarity between words, there's a relationship between surrounding words and the meaning of the words. So what they did was they said, we are Google, we have access to, all the web, all of this text, and we're going to build this type of neural networks. The input is, let's say, a given word, and there's this notion of a skipgram. We are skipping over certain words, and then we are going to try to predict some of the surrounding words. So that was the idea. And so how does it work in practice? You one hot encode your input. Chased in this case may have a representation of the form 0001, and then dog might have a representation of this form, the cat representation of this form. And so you're interested in modeling the probability of dog and cat given the input, which is in this case is chased. And you can make conditional independent assumption, and you can write it as a probability of dog given chased times probability of cat given chased. And so now you have a probability model, and you can actually learn the parameters of this neural network to maximize the probability of dogs and cats given the center word chased. So that was a learning problem for the neural network. Find W vector that maximizes the likelihood of dog and cat given chased. And just now imagine doing this at the level of the entire text that exists on the internet, or all the text that exists in Wikipedia. Replace dog and cat with any other word, and with a chased by the word that surrounds them. So they trained that, and the way they did it, I'm going to simplify it a little bit, but let's say you push it through the network. The weights of the network are randomly initialized, and it produces the output like this, a numerical output like this. And the highest probability word here is chased, but it's supposed to be dog. The highest probability word here is, tiger, but it was supposed to be, cat. And so that defines an error or loss, the difference between what you expected and what the network produced. That's called the loss. And so what you do is you come back here and you try to tweak the parameters W so that the loss is minimized. So I don't know all the backgrounds here, so I'm very briefly going to talk about how you minimize losses of this form in neural networks. So here is a simple example. You have a simple neural network. You have Z's that are a function of your W's, and then you have the L that is a function of the Z's. And so if you are trying to figure out how to establish the sensitivity of your output with respect to the input parameters, all you need to know is essentially calculus tree. If you recall, there was this notion of chain rule from calculus, that if you have a function, in this case, let's say Z is a function of W, and then L is a function of the Z or function of G of W, it turns out the chain rule in calculus allows you to take the derivative of G of W with respect to the W. It turns out the chain rule says you have to take the derivative of your output with respect to the intermediate variable Z, and then the variable Z with respect to the W. And you can do the exact same thing for in the case that your inputs are like vectors. If you have vector W, and these are the weights in the neural network, and then there is some function that gets applied to that. There is this notion, we call it gradient. At the end of the day, chain rule allows us to figure out what the sensitivity of output is with respect to the input. In particular, this notion of gradient tells you in what direction, if I change my W's, I'm going to see the largest increase in my loss function, okay? So a little bit of flashback to undergrad. Okay, why is that useful? It turns out, I told you earlier on, you want to minimize the loss function, right? The network makes a prediction about the words, and you want to minimize your loss function. If you know the gradient is always in the direction of increase in the loss function. It turns out if you go in the negative direction of the gradient, you can find the minima of a function, or you can now minimize the loss. So the loss here, which is the difference between what you expect from the neural network and what you observed, is a function of the parameters of the network. In this case, I'm showing two of the parameters, W1 and W2. And essentially, this notion of gradient descent allows you to start from a random location, a random initialization of weights, and follow the direction of gradient and find the minimum of the loss. It turns out in high dimension, it's a little bit more difficult, and you may not find a local global minima. You might find a local minima, but it turns out when the dimensions increase, actually the problem becomes a little bit easier. There are, I'm not going to get into the geometry of higher dimensional spaces, but it turns out this very simple gradient descent equation allows you to, in an iterative fashion, to minimize your loss function. And so going back to this model, now we had the ability to kind of use gradient descent to tweak the parameters of this simple neural network to do this simple task of predicting the sort of the words dogs and cats from the word chased. And so once you do that, then this neural network has this internal, what we call the hidden unit. And the hidden unit of these networks are typically in the order of maybe 300 or 400 versus our vocabulary, as I mentioned, is typically order of 10,000 or 30,000. So these internal representations, so you push in the one hot coded for chased, you get internal representation, which is the activation of these neurons. And it turns out those representations, they have really interesting properties. So let's look at that. By the way, when this came out in 2013, I was doing my postdoc. We were sitting in a room with my professor at the time, and everybody was amazed that just such a simple modeling would allow you to come up with this representation. It turns out you can have the vector representation of the king and the queen, and you can do some sort of simple linear algebra to say, if I have the vector representation of king, if I subtract from that the vector representation for the man, and then add to that the vector representation for woman, the resulting vector points at queen. So it turns out some of the semantic relationship between the words that gets embedded in the activation of the neural networks. Similarly, people realized soon that you can do certain analogy type of work with these network representations. You can get the word, let's say Spain, subtract from that Madrid, add it to Italy, and it would give you the vector representation for Rome. So the neural network was able to encode relationships. And these are all from a very simple modeling of trying to predict surrounding words from center words. So that was the idea of word vector representations, which essentially allows you to, for every word in English language, you can come up with a, let's say, a 300-dimensional vector that represents that word, and that the geometry of that space captures something about the meaning of the words. All right, so here we are, 2015. My team actually tried to do some of this modeling with electronic health record. We had data from the publicly available MIMIC database, and we had roughly about 126 million words. These are clinical notes from the MIMIC database. And we had this simple question. I'm not going to get into details. The question that we had was, is there a way for us to characterize this sentiments of clinicians, whether the clinician who wrote the note was optimistic or pessimistic about the patient? And would there be any relationship between the sentiments of these notes and outcomes of the patients? So what we did was there was a database of sort of positive and negative words, and we converted those, like words such as good, happy, better, being positive, etc. We applied word to vec, and we came up with the vector representation of those words. Then within the clinical notes, we also tokenized and we converted all the clinical notes to a corresponding vector representation. And then whenever we had a new word, we asked the question, is there a positive or negative word in the neighborhood? So because now you have vector representations, you can do a k-nearest neighbor search to find the most closest words to a given word. And using that approach, we essentially assign a positive or negative sentiment to every sentence and every paragraph and every note in the electronic health record. And once we did that, we broke it down for patients who survived versus patients who died. And it turns out you start on day 1 in the hospital, and among the patients who died, the sentiments are sort of, it's still maybe somewhat positive, but is in the lower than patients who end up surviving the hospital. And as you see, as the time progresses, by day 3, the sentiment becoming negative, and they sort of plateaus. In particular, if you look at patients who died versus survived, the sentiment tends to be more negative, and then sentiment to become exceedingly negative for patients as they get older and older. So these are sort of the underlying sort of positivity or negativity of the clinician's note regarding those patients. And then we had a follow-up paper. We looked at if you look at utilization of imaging in the hospital, we wanted to know if there is any relationship between the sentiment of a clinician and how many CT scans they order. And it turns out if there is positive sentiments, over here, the utilization was a little bit lower, versus if there was negative sentiment, the utilization was above the sort of the population average. So that was kind of interesting. And the reason we looked at this problem, we had a radiologist who told us, ordering of imaging is very much provider dependent, and he was wondering what could be some of the potential factors. Anyway, so word2vec really allowed people to convert text into numerical representations that then they could push into classifiers to make interesting classifications. All right, but the search for meaning continues. And it turns out, yes, it is true that meaning of word might be related to the company that it keeps, but there is, ordering into words. If you look at the, word, the dog chased the cat, or the sentence, the dog chased the cat, versus the sentence, the cat chased the dog, from the point of view of word2vec, they have the exact same meaning, because word2vec doesn't really capture anything about the ordering of these words. It's just trying to predict the surrounding words from the center words. Here's another example. The stolen car sped into the arena versus the clown car sped into the arena. The first one is serious, and second one is supposed to be funny. So if you're trying to classify these sentences in terms of their sentiments or in terms of their meaning, it turns out something like word2vec doesn't work, because it's not taking into account the ordering of the word or the context of the words. And that's where people start thinking about language as time series. And there were two competing methods, the convolutional neural networks. These are actually the methods that around the same time they became super popular in classification of images. I showed you an example earlier on. And then we had the recurrent neural networks that were specifically for time series. And so recurrent neural network, the idea is that if you're trying to find a relationship between some input and output, there's a hidden layer that maintains the history of previous elements in your sequence. And so here's an example of that. Again, the example of the stolen car split into arena. A recurrent neural network, if you unroll this in time, basically you have a hidden unit now associated with every word. And when you are trying to come up with your label or classification, you're taking into account the entire sort of history of what has been said. It turns out the same idea of gradient descent that I mentioned earlier on applies to this type of models. If you have a sentence and your desired output, let's say in this case is funny, but the label that the model is producing is serious, and that's an error, you can actually backpropagate that error through this network and fine-tune the parameters of the network using the same idea of gradient descent that we had. So people came up with several different variations of these recurrent neural networks. There is a one-to-many variation where you have as input your one-hot coded representation of the word, and then you could go from there to multiple inputs. And then there's a classification part, which is, by the way, this is an example that you could prompt a network and it produces a text for you. And I will get into that in a bit. There's another variation where you have multiple input and it can be mapped to a single output. This is useful anytime you have a sentence and you want to classify that sentence. And then there's another variant, which is called many-to-many, where you have a sequence of words, maybe a sentence, and it goes through the network, and then it produces, at the very end, another sequence of words. And this can be very helpful for Q&A type of thing. You ask a question, and then the network produces a response. And then you have another variant of this many-to-many, which you have inputs and you have outputs. And it turns out this variant is helpful for machine translation. You go from English to German, etc. All right, so what is sort of the mathematics background behind these recurrent neural networks? So it turns out in the regular neural network, you have some input. We call it your features or the one hot coded version of the word, and you go straight to the output. With recurrent neural networks, you have, as I mentioned, these memory cells. So anytime you have an input, it gets multiplied by some matrix, and then the information from the previous unit, let's say you are sitting here at Y3, and you have this internal state. The internal state is a function of the input, but also is a function of the memory from the past. In this case would be S2. And then your output, Y3, is a function of now the state. So because of this architecture, these models are able to carry forward in time the information from the past in order to make a prediction. But it turns out with this type of models also, if you have a desired output at this point, let's call it Y3, and you have a predicted output, you can calculate the difference and you can pass the gradient through this network and fine-tune the parameters of this network, in particular here U, W, and V, in order to sort of teach the network how to produce the right output. So that was the notion of sequence-to-sequence mapping. I'm not getting into all the details. Really, I'm trying to give you a little bit of historical background how we got into large language models. All right. But this type of models, they did have a problem. It turns out if you are trying to pass the error information to, let's say, get the sensitivity of the output with respect to these parameters, as you pass it through a number of different steps, you're multiplying a bunch of matrices together, and it results in either information sort of exploding, is the notion of exploding gradient, or the matrices, when you multiply them together, the resulting matrices become smaller and smaller, and that's called the notion of vanishing gradient or loss of memory. So it turns out these networks, they had limited capacity to recall information from the past. Having said that, they found quite a bit of success. This is from 2013. There's a nice website that is still active. I checked it yesterday. It's still active. That was allowing you to type in something in English, and it would return the equivalent in a handwritten style. So the input here would be the series of words in English, and the output would be the corresponding characters in a different handwriting style, and it was able to generate very nice sort of images. So that's 2013 was fun to play around with that tool. And so these methods of sequence-to-sequence modeling that included sort of an encoder where you have your sequence of words as input to recurrent neural networks, and then you kind of get the state of the neural network, the hidden state activation, and then you push it into another network to act as a sort of a prompt, a starting point to generate a sequence of output words. That became kind of the standard for a while for generating text. So as you recall, with word vectors, you are looking at compressing the meaning of words into a single vector. But with this type of models, you are trying to compress not only a word, but also the entire context and the ordering that occurs in a sentence into a given vector that then can be used to generate text. So here is one of the famous figures in this domain. People were trying to do machine translation, and there is a score called the BLUE score, which is a number between 0 and 1 that measures the similarity between a gold standard reference translation and the machine translation that is produced using this type of architectures. And when people looked at different model architectures, and they noticed that depending on the sequence link, there is a drop in the performance of the BLUE score. And that was because of this vanishing gradient problem that existed with these models. So around that time, this paper came out. If you recall, with the initial Word2Vec, Joshua Bengio, he was the first author. He never gave up. 2015, he had another paper called neural machine translation, and he introduced this idea of attention. So what is attention? The notion is that with something like a neural network, there are different variants of that. A recurrent neural network, there are different variants of that. One of them is this LSTM. Let's say you have a sentence in Chinese and you're trying to translate it to English. It turns out there may not be a one-to-one relationship between the Chinese words and the English words. And so you need a way of, depending on which word you are trying to translate, you need to have a way of putting more emphasis on certain locations in the sentence. So the arrow here is essentially showing the contribution of different hidden states of the recurrent neural network, or in this case, the long short-term memory, to given translation tasks. So this type of networks, they had a built-in what is called attention gates that looks at the entire history now of a sentence and figures out which part to attend in order to make the prediction. So I'm not a Chinese, or Mandarin speaker. If anybody here knows, might realize that there's the network is actually able to put the right emphasis on the right characters when it's trying to predict a term, let's say machine or love in this case. So attention became quite important in any task that involved mapping a sequence to another sequence, but the alignments are not clear, and you have to learn that in a data-driven fashion. All right, so a lot of these type of things happen in parallel in different fields. At the same time, folks that were working on deep learning for visual object recognition, they were also trying out different ideas. And what they were really interested in was if algorithm is looking at this picture and says there is a woman in this picture and there's a frisbee, what is it really that the algorithm is looking at? So they were playing around with this notion of attention. And then there was an interest to generate captions for images in an automated fashion. And so the people were playing around with these different ways of passing different patches of these images to these recurrent neural networks and having them to come up with labels. And here it is showing that this attention mechanism, whenever it's generating the label frisbee, is actually does pay attention, or that's the area where is getting more weight in the network. So that was interesting. That this notion of attention also was important for visual object recognition. So people started applying these techniques to generating text for medical images. Here's a paper from 2017. They said, we can actually use a similar type of recurrent neural network to generate text. And in this case, the thought vector, or the vector that you use to prompt it, is essentially comes from passing your, let's say, chest X-ray through a neural network and coming up with a numeric representation of the chest X-ray that then you can use it in association with a prompt, a question to generate, let's say, a description of the image. And so that when you're doing that, also the notion of attention turns out to be super important, because if you have a chest X-ray, the findings that you're interested in are often localized in certain areas. So attention became a very important part of these neural networks. All right, this brings us to this seminal paper in 2017. These authors, also from Google, they came and said, we can get away with just attention. We don't need anymore those recurrent neural networks type of things. So the title of the paper was "Attention is All You Need." And in this work, they came up with this model architecture called transformers that became really the foundation of modern machine translation. ChatGPT, all the large language models are using this architecture. So what is this? So, all right, let's walk into this, and this might require a little bit of additional explanations. So the basic idea behind this was you have an input and you have your output, and you are sort of coming up with some encoding of the input, and you are trying to accomplish certain masked word prediction tasks. Again, going back to our example, check the program log and find out whether it ran, please, versus check the battery log and find out whether it ran down, please. Whether the word ran comes here or ran down depends on a word like program or battery much earlier in the sequence. So they said we can actually solve this type of prediction tasks. You can mask this word and ask this type of networks to predict what word should come here. And we can do it without the need of anything else but attention. All right, so they introduced two building blocks here. The first building block is called the encoder building block. And the encoder building block has what is called a self-attention. In fact, there is multiple self-attentions, and that's what is called multi-head attention. So what is a self-attention? So the self-attention essentially allows to evaluate the link between the elements of the sentence, for example, a noun and a pronoun. For example, like program or battery and it, right? When you say, check the program log and find about whether it here really refers to program. And so if you want to know what word comes after that, you need to first make an association between this it and program. And then you know that for programs run, all right? Versus this it refers to battery, and batteries, they run down. So the self-attention basically allows these networks to figure out the relationship between pronouns and the nouns that occurs before them. And so in this architecture, they utilize self-attention at the input layer to accomplish that. And then for prediction of output, also they have a self-attention that is applied to whatever you are trying to predict. But then they also introduced what is called a cross-attention. The cross-attention essentially allows the link between encoded and decoded elements. So in this example, the link between program and the masked word ran, or the word battery and the masked word ran down. But the link is really through the word it over here, that once you know that it is connected to program, the cross attention allows you to say, okay, the word ran should come after. So the building blocks are as follows. You have self-attention, and then there is something called add and normalization, which is a way of controlling this problem of vanishing and exploding gradient that I mentioned earlier on. And then it goes into feed-forward neural network. There is another sort of normalization going on. And the output from that goes to this cross-attention. The same thing happens to the output that you're trying to predict. You have the cross-attention, and then there's a feed-forward neural network, and you make the prediction. So we can sort of dig a little bit more into this. The attention model here is based on this notion of key value and query. And you can ignore this. Essentially what is happening, you have the input, the words are going into the network, they get mapped into what is called a key and query. And then there is a transformation of the input that shows up over here. We call it V. For all practical purposes, you can think about the V actually as the same as the input. So the input, the dimensionality is dimensionality of embedding of the words, and then the number of tokens that you have. So if you have a sentence that has 10 words, this particular matrix has 10 rows, and then each row corresponds to embedding of a word, representation of the word. So for a second, you can imagine that this, just ignore this, and the V are exactly the same as X's. What is happening over here, based on the input sequence, you have these key and query values, which once you multiply them together, they give you a vector of the same length as the number of tokens that you have. And it corresponds to essentially how much weight you should put on every single token in your sentence. So here, essentially what you do is a dot product. The V's, which I mentioned, is the same as the X's, or essentially has a dimensionality of the embedding and the number of tokens. Once you get, it gets multiplied by this quantity over here, certain tokens or certain words, they get more emphasized in the resulting vector. And that's what is being passed to the next layer. And you can do that multiple times because you have multiple of this type of attention mechanisms. So, okay, let's look at how that looks like in practice. Here's your sentence, you know, the law will never be perfect, et cetera, et cetera. And the self-attention essentially allows you to figure out the relationships. When you say the law will never be perfect, but its application, you know that it's, in this case, is referring to law and application. And so it's able to encode those kind of relationships. It's a little bit magical, but once you feed it enough of data and you train it in a what we call unsupervised fashion on masked sentences, and it tries to make predictions of those masked words, the network is able to find this type of associations. So it turns out transformers, they became sort of the standard for this field, and now they're being applied to all sorts of problems. But you know, that was the first success story. It turns out I mentioned the BLUE score, which has to do with machine translation. They came out being as the state of the art. I believe this was a 2017 paper, and not only turns out they were performing very well in these types of machine translation, but also computationally, they were less expensive in terms of number of computations that needs to be done. Computationally, in order to train these networks, you needed to do essentially an order of magnitude less computation. And that turns out to be one of the defining factors for these models sort of winning over all the prior models that existed. All right. So once we had these transformer building blocks, people started coming up with different architectures. So here is the so-called the BERT model. The BERT model essentially stacks the number of these transformer layers or models, and both sort of vertically and horizontally. And you have your input tokens here. They go through different transformer models, and you are trying to come up with prediction at the output layer. OpenAI at that time, again, this is 2018, they came up with their GPT model, which was making use of the transformers, but in a causal fashion. So if you look at the arrows here, and a sentence going from left to right, this model only has access to information from the past and never information from the future. And this turned out to be super important if you're interested in generating texts, because texts are typically generated in a sequential fashion. You ask a question, and the network comes up with the first sort of word as a response, and that word becomes the input to the network. But the network has access to the context, etc., and it generates, this subsequent text. And then there was this Elmo model that kind of is, stuck with the old recurrent neural network architecture and was competing with the BERT model, which was based on the transformers. In terms of parameters at the time, the typical recurrent neural networks, they had about 10 million parameters. This Elmo model had 90 million. GPT, the first generation, had about 110 million parameters. BERT had 320 million, and GPT-2 came out, which was groundbreaking. It had 1.5 billion parameters, groundbreaking for that point in time. All right. So the way the BERT model was trained was also using the similar approach of masking. So you have a sentence, you mask a couple of words, and you ask it to predict the masked words. So again, going all the way back to word2vec, they were trying to do something very similar. The only problem was that those networks, they were not able to capture the ordering of words, the context of the words, and also the alignments of the inputs and outputs, because there was no notion of attention. But now we had attention, and we could solve this type of masked words problems quite efficiently and perform translation from one language to another language, even though in the other language, the alignment of words are different, or even the length of the translation in terms of number of words are different. We are able to solve this. Okay, so around 2019, people said, why don't we fine-tune these models on data from PubMed, and that's where you start getting the PubMed version of the BERT, or in some clinical databases, and that's where you start getting like clinical versions of the BERT. The idea is that you start with an existing BERT model that is trained on the content of Wikipedia or the entire internet, and then you go and you fine-tune the model on PubMed so that the model becomes better at understanding scientific language or bio language. All right, so here's an example of application of these models. This is actually based on recurrent neural networks. 2018, it wasn't really clear again who is the definite winner, so people were still using LSTM, and this particular model was used to tag notes, sentences in clinical notes in terms of whether they are PHI, protected health information, or not. So the PHI categories are shown over here. And here's an example. Patient is 67. And the inputs that the model is producing is not a PHI, not a PHI. Okay, 60 and 7, they are example of PHI. Age is a type of PHI. So these models, they become pretty good at identifying PHI and then masking those to sort of identify the PHI. Then came this model called MedBERT. MedBERT is essentially a transformer BERT architecture that was trained on 28 million patient records from the Cerner Health Facts database. So this particular model was essentially all the clinical notes were shown, and they performed one of this masked word classification type of approach. And they wanted to know if you have the clinical notes and apply the BERT model and extract the activation of neurons in the last layer. Those are called the embeddings. Can we use those to perform your classification tasks? So they focus on two classification tasks: prediction of heart failure for diabetes patients and prediction of pancreatic cancer. And they showed that making use of the embeddings or the representations from the clinical BERT results in improvement in AUC. Here is another paper in 2019 that trained the BERT model, but on the publicly available mimic database of intensive care unit patients. So these patients arrive in the hospital, and there is triage note, and there's follow-up clinical notes every few hours. And they ask the question, can we use this data set to fine-tune the BERT model and then apply it to a number of tasks, such as generation of summary for discharge summaries for the patients, or performing some classifications. So this particular model, my team, we made use of this model for some of the classification tasks that we do in the lab, and they are quite powerful. It turns out access to these models, they became very easy through this website called Hugging Face. Hugging Face allows you to access these models in just a few lines of code. So here's an example. You are trying to make use of all the radiology notes, nursing notes, physician notes, etc., to make a sequential prediction about the risk for readmission. And so let's just quickly go through this. You import your transformer model from the Hugging Face library, and the particular type of transformer that you're importing is the bioclinical BERT that is fine-tuned on the mimic database. And then here's the example of note. Patient had severe headache. It's a simple sentence. It turns out you can, there's something called tokenizer that maps the words into some underlying tokens that then are fed into the BERT model. And you can actually look at how the output looks once you tokenize this. It turns out tokenizers, they can break down words into multiple sort of subsections, but you end up with a series of IDs. These IDs correspond to 101 is the beginning of the sentence, 102 is the end of the sentence, and everything in between are the IDs for different tokens, sort of the subwords that you come up with. So in this case, you have 13 tokens corresponding to this particular sentence. And you can actually look at the output of this BERT. The output for this 13 token is a vector of size 768. That's the hidden representation that the network learns. And this hidden representation is essentially very similar to word2vec, is something that you use to throw it at your classifier to make these kind of predictions. So if I have a sentence of this form, I can essentially get my 768 dimensional vector representation, and I can take the average, and now I have a single vector of 768 that kind of has is a representation of this sentence that I have. I can do a similar thing if I have a paragraph or if I have an entire document. And that, again, resulting vector representation is what goes into this type of classifiers for making predictions. So again, with the emergence of these websites like Hugging Face, doing this type of task became much, much easier. with a few lines of code, you could encode your clinical notes, and you can pass it then to a classifier to make predictions. All right, so people start incorporating this type of transformer agents into mobile apps to build conversational agents. So here's an example of conversational agent. It was a COVID-19 assistant agent. It says, hi, how can I help? And it says, just came back from Rome and have a cough. Do I need to be quarantined? And it says, so it's basically having a conversation with the patient. Around the same time, this Paris-based company, Nabla, basically asked a question that can be used, one of these models. At that time, we had the GPT-3 out, and they said, can we use it to provide psychological support for patients? And this became controversial because the patient says, hey, I feel really bad. I want to kill myself. And the ChatGPT, or in this case, GPT-3 said, I'm sorry to hear that. I can help you. And the patient says, should I kill myself? And it says, yes, I think you should. So here was the problem. These models, they were producing outputs that there was really no safeties built around them. And that became very, very concerning. So this jump started entire research into how can we make these models who are generating text, safer to use. All right, so that brings me to what is really the large language model. So at their heart, they are based on, most of them are based on some variants of these transformer models. These are general purpose models that are able to model sequence of words that appear in a sentence, and they have a good notion of what is the next word that is statistically most likely to show up, given some context that we are providing there. And they are trained on massive amounts of content from the web. And they use a combination of methods for training. They often are trained using that masked word prediction task that I mentioned earlier on. But because of safety concerns, people started to introduce another approach, which is incorporating feedback from human beings into training of these models. And the way you do that is through what is called model fine-tuning using reinforcement learning. In particular, this is called reinforcement learning with human feedback, because the companies, they realize that they really need to hire a group of human beings to look at the output of this type of models and rank them in terms of harm, or in terms of usefulness, or in terms of politeness. And once you have those feedbacks, you can learn a reward function. A reward function essentially goes from a response to how much value you are putting on that response. And once you have that reward function, it turns out you can go back in and influence the probability of certain words or sentences being generated to get the type of responses that we deem as being more useful. So OpenAI, for instance, they use crowdsourcing, and they found workers at sort of pretty cheap amount to go in and rate the responses produced by their system. And then they utilized this notion of RLHF to fine-tune the model. And that really, if you look at the history of GPTs, starting for GPT-1, 170 million, GPT-2, you have 1.5 million, GPT-3, you have 175 billion parameters. Again, these are the weights in that transformer model that we talked about earlier. Really, what changed from GPT-3 to GPT 3.5, this is for those of you who started playing around with these large language models around December of 2022. Really what changed, it wasn't the number of model parameters, it was this application of RLHF, which resulted in these models producing texts that are preferred by human and are aligned with what we expect to kind of hear and see. And obviously, the models, they did get better over time with GPT-4. Now we had, 1 trillion parameters, much larger number of parameters. But this RLHF never changed. It's something that became integral to fine-tuning of these type of models to produce human sort of aligned or desired type of outputs. Here, another table from Wikipedia is looking at the different GPTs, GPT-1, 2, 3, 3.5, and 4, and looking at where the training data came from this model. So at the GPT-1, you had about 4.5 gigabytes of text from 7,000 unpublished books of various genres. GPT-2 is now looking at 40 gigabytes of text. By the time you go to GPT-3, you're crawling through the entire web, and you have this massive amount of text data that you are training. And then we have no idea what happened after that in terms of the training. You're using increasingly more and more data, but the OpenAI, the company behind ChatGPT, essentially was no longer open, and they closed down, and they decided not to disclose. And one of the reasons, as we're going to get into that, is because of the fear of lawsuits, because there's a lot of copyrighted material sitting on the web. And if you're ingesting those copyrighted material, training your model, it raises a lot of legal issues. All right, so this brings me to this notion of prompt engineering. So here is an example of a clinical note. This is made up, so there is no PHI involved, but it produces sort of a background about the patient. This patient comes in, has temperature being 38.8, pulse being 120, lactate is like 2.1. There's some contextual information in terms of physical impression or physical examinations, physician's impression, and some other backgrounds about this patient. And so here is an example of how you interact with this model. Here's a prompt that says, you are an ED doctor in charge of identifying the following abnormal signs and symptoms. It turns out these models, they can take on different roles. And if you want them to talk in certain ways, or if you want them to provide more domain expertise, you can actually prompt them and so that they assume different roles. So here saying that you're an ED doctor and you want to identify the following signs and symptoms: positive COVID-19 test, fever, elevated lactate. And here says, think step by step, and if any of these abnormal signs and symptoms are present in the following note, then return them as a Python list. So you can actually force the output to be in certain format. So the note goes next over here and corresponds to what we have over here. And here's the output that the model produces. It says, I was able to read through this, and I think this patient, in terms of COVID-19 test, fever, elevated lactate, this patient does have a little bit of fever, and returns that as a symptom, and provides a little bit of explanation that the temperature is 38.8, normal body temperature, or the upper limit should be this, and then it says, lactate level is 2.1, which is just above the normal range, but it's not really significantly elevated. In some clinical task, lactate of anything above 2 actually triggers certain protocols. And so if you wanted to return that as a sort of abnormal, you kind of need to teach it. This is an example of one-shot teaching, that you say elevated lactate corresponds to lactate greater than 2.0. And once you run it with this guidance, it actually does grab this and tags it as elevated lactate. So that's pretty impressive. So you can use, this is very simple. You can use this to, find out what are the interesting concepts or sign or symptoms that you're looking for in a clinical text. All right. So I really like this paper by Eric Horowitz from Microsoft Research. Basically, it says, if you want to get this model to behave as you expect, you need to really work on your prompting. And they talk about a few different approaches to prompting. One of them is called in-context learning, which essentially, as a part of your question that you're asking or your prompt, you provide some examples to the algorithm. So this was actually a task about MedQA, is a series of medical question answers. And what they showed was as you perform a few shot training, or as you start searching for, let's say, similar examples in your training database, and you provide those examples as few shot examples to the large language model, you essentially start getting better and better performance. So this notion of in-context learning, again, has to do with providing some examples to the large language model, but there is also this notion of chain of thoughts, where you break down a harder problem in terms of smaller problems, and you ask the network to think step by step to solve that. So if you recall, in my previous prompt, actually, I said, think step by step. And then there is this notion of ensembling, which allows you to run the same prompt or similar prompt multiple times, and then check for consistency across multiple runs to make sure that the results are consistent. And so what they showed, that if you start with a large language model, as you introduce a few examples and as you do this ensembling, that's where you get the best performance out of the this particular quiz, the MedQA, type of quiz. Yes, yeah.
Real quick, don't know if this is a good time for you now, but Beth had a great question.
Yes, go ahead.
Chat was hoping. Beth, do you want to unmute and ask, or I can ask? Are you there?
Yeah, I'm here. And yeah, I don't mind asking. I listened to a story recently where these kind of big models are running out of like human generated data, and that there's discussion around kind of feeding generative models the data that they create. And so just curious if you kind of heard of this and sort of the impacts that this may have, just around running out of human generated data, and what could happen.
Yeah, that's quite interesting. So this is a very active field, and you see a lot of papers showing up on arXiv. So the answer I'm going to give is probably not the most definite answer, but what people have been observing is if you give them synthetic generated data, the performance actually can go down. With the exception is if the generated data is from certain domains, fields that those corpuses of text are not available in the internet. Let's say, again, you're interested in patients in your hospital, and hopefully the data from those patients is not available on the web. And so you want to train one of these models, but again, because of PHI concerns, you don't want to fit the data as is. You want to generate some synthetic version of those clinical notes. And in those cases, these models, if you want to specialize them in terms of understanding the clinical notes from your hospital, there might be some value in the fine-tuning them on synthetic data. But if you're using synthetic data that already is present on the web, the finding seems to be that the performance doesn't actually improve, and it might actually get worse.
So are we running out of data, or is OpenAI now and others sort of beginning to look at content generation from different companies, or what's your thought on that?
Yeah, again, I think we are out of the type of data that is publicly available on the web, but different organizations, they do have their internal databases, and so you could argue that there's value there, and people who have those massive forms of data, they could work with groups such as OpenAI and generate additional value for their organization by fine-tuning those models to their own data. Honestly, the first time I interacted with ChatGPT, I asked it the question. I said, generate a specific aims for a grant that I was working on, and I was shocked by how accurately it was able to structure the specific aim for the grant. that was early 2023. Since then, these models, they especially the free versions of them, they don't behave quite as well. You have to go and subscribe, and the subscribe versions, they perform very well. But the question I had was, how did the model get hold of so many grants, NIH grants, to be able to produce such a structured and precise sort of specific aims? It was able also to generate pink sheets. It was able to generate, like, it was fascinating. And definitely, we don't have that many grants or proposals sitting on the free internet. So these guys might have access to other data sources, and that raises a lot of issues around, privacy. And I'm going to get into that. There has been lawsuits. A lot of these documents are sitting on shared drives, and nobody really reads the disclaimers about putting data on those drives. Maybe the companies cannot access the text as is, but what stops them from accessing a representation, a numerical representation of the text that then they can use for training this type of networks? So yeah, I would say that, yes, maybe they are running out of data that exists publicly on the internet, but there are a lot of private repositories, and there is still room for utilizing those for training. Any other questions? All right, just wanted to mention this. There's a huge competition going on between different companies right now with OpenAI, ChatGPT, MedPalm from Google. And basically what these guys they have shown is the best performance you can achieve is any one of these models is really through proper prompting of these networks. All right, so that brings me to this problem of confabulation or hallucination. So large language models, by their very nature, they are trying to predict the masked word or the next word in a sentence. And they do it in a statistical fashion. They say what is the most likely. And because of that, they can have this problem of hallucination. And so I asked ChatGPT, or the co-pilot version of that, which is embedded into Microsoft Bing, tell me about examples of hallucination. And here it comes with a list of cases with large language models. They can make errors. I actually had a hard time to find the example that it actually hallucinates. The reason is that most of these modern large language models, when they come up with the answer, they also are now looking for references on the web. And if they don't find the right references, they may say that, hey, I don't know enough to comment about this. Having said that, I finally found one. So here is the example. Let me go back here. And it was, in what episode of Friends did Joey eat too many marshmallows? And it turns out there's none, but it actually confabulated or sort of hallucinated. It came up with some random episode. And interestingly enough, it comes up with a reference. And if you go to that web page and search for the word marshmallow or Joey having eaten too many marshmallows, you find nothing. So it's still these models, they have sort of these examples of this, the hallucination. And so there are a number of ways to avoid that. One of them is to actually get a second large language model and ask it to verify the response from the first one. And that tends to be a good way of reducing hallucination. Another approach is this notion of retrieval augmented generation, or RAG. So very briefly, the idea is that you start with your document, and this could be like, let's say, your local repository of text that you have, and you split it into chunks, and you get the vector representation of each of these chunks, and you push it into a database that we call a vector database. And then when somebody has a query, that query, the question gets also embedded, and then you do a k-nearest neighbor type of search to say, what type of information in my database is the closest to a query that was asked? And that provides a context. So you have now your prompt, which has the query, the question that you asked from LLM, and then the context is what was retrieved from your database in terms of the closest matching information. And you combine them together, you present it to the large language model, and then it generates response based on that. And that tends to be quite powerful. So RAGs essentially allows you to integrate LLMs with external data via APIs and enables information retrieval, allows you to kind of verify facts and reduce confabulation. You can do it with ChatGPT, with Bing search. We just saw an example of that, and it wasn't that glorious. You can do it with like Wikipedia. You can do ChatGPT with your own data. And here is actually an example. So you have your clinical note here. 28-year-old, previously healthy adult patient, presented with tachycardia, fever, mental confusion. The symptoms started after a cut to his leg while gardening. It turns out I can grab this clinical note, and in a few lines of code, I can generate a vector store. These are all courtesy of LangChain, which is, you guys should check it out. They have very nice utilities for doing this type of work. And then here's my template. Answer the question. The question is over here based on the following context. And this context essentially is what is retrieved from the vector database. So here's a prompt template. So this is the prompt. And there's a chain that it allows you to parse the input, pass it to the LLM. And then you have the prompt. And this prompt is augmented with the context, which comes from the vector database that includes this. So now I can ask this question. This is the question. What is the location of the cut? This question goes into this part in the template. The context, essentially by looking at this and searching over this sentence, is able to retrieve the important parts of this sentence, and the context goes over here. And this becomes the overall question that you're asking from the large language model. And if you ask that question, it actually comes up with the response the cut was to the patient's leg. So that's pretty amazing. You can create these sort of general purpose templates with vector databases, and you can answer really sophisticated type of questions using this approach. All right, and then I can ask the same question, what is the location of the cut, but use the language Spanish to response. And it actually comes back, and for those of you who are Spanish speakers, it comes up with the same response, but in Spanish. So that's pretty impressive. All right, very quickly, there has been a number of lawsuits in this domain because of issues related to copyright. In particular, the most famous one is Times Magazine sued OpenAI, saying that in their training, they use a lot of copyrighted material from New York Times that was on the open web. So that lawsuit is ongoing, and there are other controversies around systems such as ChatGPT. They are generating copyrighted material, things that resembles other people's work. And the counter argument to all of this is the fair use debate, which allows limited use of copyrighted material without permission for purposes such as critique or comments or reporting or teaching a scholarship research. And so courts are sorting through this currently. And this is from Deloitte, is talking about some of the opportunities that exist in this domain. Automating some of the document generations. If you are trying to come up with a protocol for your clinical trial, maybe you can start with a template and say, based on this template, can you adapt this to the following study? In my experience, these models are not quite there yet, but they do provide a good draft, first draft. So maybe something to look into, but always read over the drafts that are produced by this type of models. And then patient engagement retention, we already looked at some examples of like conversational agents, etc. They are talking about regulatory and quality submissions. In fact, we do have a project at UC San Diego right now with, as you guys know, there are a lot of quality measures and quality reporting that happens in hospitals. And they involve very extensive, time-consuming chart review by nurses. And it turns out much of that can be automated using large language models. A typical quality measure for hospital, it might include, let's say, 50 questions that you have to go through the patient chart to extract the answer to those questions. But combination of retrieval augmented generation, right prompts, and prompt engineering, it turns out you can do a very good job of answering those type of questions and save a lot of efforts and time in terms of chart abstraction. All right, they do mention here that recognize that the task is not the same as a job. a job typically involves multiple tasks, but also involves workflow. And currently, our AI systems are really good at doing limited type of tasks. I want to mention this paper that also came out of UC San Diego. They looked at the comparison of physician-generated response to patient questions versus a chatbot generated one. And they showed that the chatbot generated responses, they received higher rating in terms of quality and empathy from patients. Having said that, this particular paper, it wasn't based on the actual text, but it was about questions that people are asking on subreddit on the public forums. But here are examples of comparison. It turns out the chat-generated responses, they were more thorough, and I guess patients, they are translating that into the physician cares about them, so that they go and, or in this case, a chatbot, so they go and explain more. Obviously, this was blinded and they didn't know who was who. So yeah, jury's out in terms of this type of things. And UC San Diego had a pilot. They rolled out this system. They did make sure to put a disclaimer in the bottom of chatbot generated response that this is actually a chatbot generated response, so that they are maximally transparent. And transparency is one of the most important factors when it comes to utilization of this type of systems. All right, I'm going to wrap up with this project we have in my lab. We got a Raspberry Pi. For those of you who are familiar with Raspberry Pis, are tiny sort of computers that fit in the palm of your hand. And we were asking questions such as, can you connect to the electronic health record and access the patient record from those Raspberry Pis? It turns out yes, because you're running a Linux operating system, you can do that. And then we asked question, can you connect to wearable sensors, different type of body-worn patches? And because all of them are operating based on API calls, you can do that. You can actually bring the information to Raspberry Pi, and you can run deep learning models like TensorFlow on Raspberry Pi to analyze that data and produce risk scores. And then we asked the question, can you also put a conversational agent on this edge computing device? And it turns out the company OpenAI has something called Whisper that allows you to transcribe text in different languages. So we looked at simple example. Here's a survey of social determinants of health in 2 different languages. And we came up with some sort of open-ended sort of responses from the patient, free text responses to each of these questions in both English and Spanish. And then we asked the question, okay, let's do the following. We get the Whisper to transcribe patient's response, and then we pass the patient's response to a large language model to map it into a structured responses that are expected, yes, no, or numerical responses. And it turns out the large language models was extremely good at mapping free text response of patients from both English and Spanish into the structural response. And here you see some of the example and the matching. And it turns out the best case that was using a cloud version for English language achieved about 90% accuracy, for Spanish also around 90% accuracy. This was about 9 months ago. Since then, these algorithms, they actually improved quite a bit. So it opens up the opportunity for more interactive interactions with patients rather than just giving them surveys. So, all right, with that, I leave you with this. I prompted ChatGPT, what a modern load health story would say about, data scientists working with, EHR, etc. And it says, yes, data is a raw material for science, and science is about pursuit of truth, but truth is not, or the data is not enough. You need something else, and that's the sort of the art of medicine. All right, with that, thank you very much for your attention. Sorry, I'm a little bit over time.